In the last video, we covered the Gibbs free energy of single component systems. In this video, we'll look at the Gibbs free energy of binary systems. We start with ideal solutions. We'll come back in a bit to define what is an ideal solution. Assuming we have two metals, A and B, and we also assume that they have full solubility. For metal A, it has its own Gibbs free energy, enthalpy, and entropy. We call them G1, H1, and S1. Similarly, for metal B, we have G2, H2, and S2. Let's start with the intuition to think about what will be the Gibbs free energy of a system mixed with A and B. Here, we'll apply the rule of mixture. Let's draw the energy diagram. X-axis is the composition. To be more specific, it's the composition of B. So on the left end of the diagram, it's 0, meaning 0% of B. On the right end of the diagram, that's 1, that's 100% of B. Here is the Gibbs free energy of pure A, and here is the Gibbs free energy of pure B. In this example here, the Gibbs free energy of B is higher than A. It doesn't have to be the case. It can be either greater or smaller than A. Draw a straight line connecting G1 and G2. Then the Gibbs free energy of any alloy made of A and B will be shown on this graph. And this is based on the rule of mixture. The question is this the case? To address the question, let's have a closer look at Gibbs free energy in terms of enthalpy and entropy. Since we're mixing A and B together, then the delta H mix will be simply H2 minus H1. The delta S mix will be simply S2 minus S1. Then the delta G mix will be equal to delta H mix minus T times delta S mix. Recall that we're looking at the ideal solution. What does ideal solution mean? Ideal solution means there's no heat absorbed or released during mixing. Therefore, delta H mix equals to 0. Then G mix is simply minus T delta S. Before proceeding further, let's have a closer look at entropy S. From statistical thermodynamics, we learned S is equal to K, then log omega. K is the Boltzmann's constant. Omega is a measurement of randomness. In solid solution, omega measures how many ways or the configurations you can arrange the atoms. Let's look at a super simple example. For a pure metal, assuming we have only 4 atoms, you only have one way to arrange the atoms like this. If you have an alloy system with 50% A, 50% B, if you have only 4 atoms, then 2 are A and the other 2 are B. In this case, how many ways we can arrange these atoms? Let's draw them out. Here, you have 6 ways to arrange the atoms, so the system has 6 configurations. In the entropy term, we say the alloy system has higher configurational entropy compared to the pure metal system. There is a formula you can calculate omega config. I will not read the equation out, and you can have a look yourself. One thing I'd like to draw attention to is that when you're mixing 2 components, you're introducing randomness into the system. By introducing the randomness or entropy into the system, you actually lower the overall Gibbs free energy. This is because G is equal to H minus ST, where S is entropy. When you increase entropy, G decreases. Again, let's draw the energy diagram. On the x-axis, that's the composition of B. On the y-axis, that's the Gibbs free energy. As we add more B into A, the entropy will keep increasing and the corresponding Gibbs free energy will decrease. When you have 50% A, 50% B, the entropy is at its maximum and Gibbs free energy is at its minimum. As you add more and more B into the system, the entropy will decrease, and when you have all B atoms replacing A atoms, the entropy contribution will be back to 0. Next, let's consider the effect of temperature. Again, remember G is equal to H minus St. As temperature increases, we can further lower the Gibbs free energy. And this will be our new curve. But again, here, the highest entropy and the lowest corresponding Gibbs free energy will happen at 50% A and 50% B. Taken together, there are two things control the Gibbs free energy of the A and B alloy. The first is the rule of mixture. Let's say that's number 1. The second is the contribution of entropy. Let's call that number 2. Combining number 1 and number 2, you have the new Gibbs free energy diagram. Here we'll use the dashed line to show the rule of mixture. The solid line also accounts for the entropy. At a higher temperature, we'll use red color lines. The rule of mixture part does not change. The entropy does not change. What changes is the T. So G is equal to H minus St. Then when T increases, Gibbs free energy also decreases. So far, we are only looking at the ideal solutions in which the mixing process does not cause any heat exchange, so there's no heat released from the system, or the system does not absorb heat. In reality, mixing is usually accompanied with heat exchange. If the process absorbs heat, it is called endothermic. If the process releases heat, it is called exothermic. Let's have a closer inspection at these two scenarios. In the first case, it's exothermic, which means delta H mix is less than 0. This is because enthalpy before mixing is greater than the enthalpy after mixing, so the excess amount of energy is released as heat. For simplicity, in the next 3 examples, we'll turn a blind eye to the rule of mixture and only look at the effect of enthalpy and entropy. Let's draw the enthalpy curve first. As we add more B into A, the enthalpy decreases because heat is released from the system. However, as we add more and more B, it's getting closer to pure B, the decrease in enthalpy diminishes. Next, we draw the contribution from entropy, which is minus T multiplied by delta S mix. Adding these two terms together gives us the Gibbs free energy curve. The exothermic case is pretty straightforward. This is because both the enthalpy change and the entropy change will lead to the decrease of the overall Gibbs free energy. In contrast, the endothermic mixing is a bit more complicated. In endothermic mixing, the system requires additional heat or energy input into the system, so the overall Gibbs free energy increases. If the entropy effect is dominant, this means the Gibbs free energy decrease in entropy is much greater than the Gibbs free energy increase in enthalpy. Then the Gibbs free energy curve will look like this. In a different system, if the Gibbs free energy increase from enthalpy is substantial, but the Gibbs free energy decrease from entropy is minor, then the Gibbs free energy will look like this. From the curve, you can see that as you add more B into A, initially there's a decrease in the Gibbs free energy, then very quickly there's an increase in the Gibbs free energy. Then as you get more and more into the B-rich end, then the Gibbs free energy will decrease again. By the end of this video, I hope you have developed a solid understanding on the Gibbs free energy in the binary systems. Equipped with this knowledge, in the next video, we'll start discussing the binary phase diagrams.